All right, this time I'm going to ask Professor Gordon Gow to come to the front. Gordon's going to speak to us about big data, and as this new sources of data are flowing through the health system, how do we make sense of it? What are some of the tools and analytic methods that need to be considered to do this? Gordon actually teaches our big data class here and has a lot of experience working with all sorts of interesting data that he'll share with you.
Anyone want to stretch? Feel free to do so, please.
So after Gordon's presentation, we'll have a short break, and then the last session of the day will be Alexis Gilroy, who's a partner at Jones Day, and she's also on the board of the American Telemedicine Association, sort of one of the former leaders in telehealth regulatory policy, and will give us a dinner briefing on what are the most current regulatory updates that are of interest to those operating in this space. So it's getting late in the day. It's got a lot of information to digest, but that's not to be missed. So with that, let me turn it over to you, Gordon.
Okay, thank you so much. I know that several have expressed sorry to me, saying that being the guy talking about analytics at 5 o'clock after a long day's program, so this is really, really difficult. Unfortunately, right, analytics means math, right? Lots of math here. I see that the blood pressure, is going up. So I promise I will not touch about math at all. So here I do want to talk to you about two important issues that being the CEO or senior manager in a company in mobile health domain that you will encounter sooner or later. So that is, you need to kind of set up the data infrastructure, right? When you initiate the project, you need to do the data crunching, and then finally you get insights, and you know how to apply those insights from data. So I guess, this is very math intensive, which you can hire smart students from our MD program and the master program. But you do need to know, right, how to start, and also need to know how to apply. So I would like to talk about the important issues related to here and the end. So here, right, is about the big data which you're going to encounter, and here is about how to apply those findings, into your practice. So the statistical challenges there. So pretty much that's it. And hopefully, there are something that we could, remember in the end. So, okay, that's working pretty cool. So first of all, right, for mobile and telehealth, so one thing that we want to know is that there is tons of data. So far, right, so all the previous presenters have did a great job, right, talking about, right, how a lot of data has been generated. And so where the data come from? It comes from all the social media applications like Facebook and Twitter. It also comes from a sensor, right? So John and Jay and Kenny, right, all give a lot of examples about sensors. So let me just add two more. One is here, right? Actually, this is a sensor that can put on your chair, where you can do, right? It can sense, right, the pressure, right? Then it can help prevent low back pain, which is a very common issue. And this one is actually related to what John is talking about, the preventing fall. So this is called smart floor, where it is going to measure, right, how you walk, and then it can kind of use all those kind of data collected to predict, right, the risk of fall. So which probably will be very useful in the future. So yeah, so basically the technology is going really fast, and what you can see is that a lot of data has been generated. So basically there are three categories here. One is user-generated data, which we're all very familiar with. Then the second is the system-generated data, like from, right, you install an app, right, you're using this app, then all your gestures and touches on the screen, and communication with other wearable devices like Fitbit. So all this will stream into some data repository where, will be part of the big data. And the third is clearly the sensor-generated data, so which is actually much, much bigger than either user-generated data or system-generated data. So anyway, so this is a figure about, called heat map, where you can see, right, how the users are using that map and using the app, right, on the smartphone. So where you can see, right, so which are the main points of the use. So overall, all these data are there, so which means that we will have a big data problem. So to make things even worse is that the mobile devices data is not enough for you to get something valuable. Rather, you need to add other data like the pharmaceutical R&D data, clinical data, and claims data together. Then you have a full picture about what's going on. So this will make the data problem even more severe in that you need to kind of bring in a lot of external data to complement what you collected from your mobile devices. So then this is where we have the big data problem. How many of us have heard about big data? I know that everyone raising your hand, right? So then how many people are kind of in this situation? So basically, right, big data is everywhere. We all heard about it, and then it seems that it's very powerful, right? It knows everything. It's magical, and we all know about these three ways, right? It's huge volume, right? A lot of variety of data, and then it's changing very fast, right? The velocity part. So seems that we all know what big data is, but then you get into kind of this situation where you see all these kind of fancy terms and weird animals like the bee head, elephant head with the bee right body there. So all these things right like HDFS right, pig, mahout, hive, scoop, flume. These are the terms right used in big data, and you see this all the time. But I guess it's really difficult to understand what they are, right? So I hope in the next 5 minutes I will make things really clear so that you can understand, right? So what these are, and then the next time you're talking to your, principal architecture, data architecture, you will be able to use these terms very, very confidently. So okay, so that's my favorite quote about big data. You probably have seen it before. So then I read. So
Ariel, started coming on CNBC now, which is not a good sign.
oh, okay, yeah, let's see that. So now let's start with the very familiar thing called the relational database, which we kind of all know about, right? So that is our way of storing data so far, the mainstream way of storing data. So basically, right, whatever you use, Oracle or SQL Server, so basically your company probably has this kind of relational database, RDBMS. So what it does is that it defines the tables, which each table is like a big spreadsheet, right? The custom table has all these attributes in it. Then this is the order, and this is the item table, the distributed table. Anyway, so why we call them relational database? Because all these tables are connected through relationship. So like customer number and customer number here, right? So these two tables are linked. Item number here is them linked, and then distribution number. So basically, through the primary key and foreign key matching, we began to be able to link the tables together and do something meaningful. For example, right, if you want to know, right, what customer, like the customer's name is John Smith, right, and then what kind of a genre he likes, then you are able to go from the name, then search get the customer number, then go to the order table to get all the order numbers, and then the item numbers, then go to the item numbers, you get the genre. So basically, this is how the relational database works. Everyone should be very clear, right? This is very easy, actually. So this was the revolution in 1970s, and these days, right, most companies are using this. So now the question is, what's wrong with this? So it has a lot of advantages, right? It's very neat, very clean, very well defined, right? The data integrity is at a very high level. The problem is that it's not flexible. When you want to write a new part of data into your database, you have to follow this strict schema that has been predefined. And then you need to have a very supercomputer if you have lots of data, because all the tables need to be indexed and linked to each other through computing. So this is where actually the most famous guy running the relational database management system, which is Larry Ellison, right? So it's super rich, right? And then this is the island, this is this yacht. You know that, right? So whenever
He actually forgot his plane.
oh, really? Okay.
On the back of the yacht.
Yeah. So this guy, right? So it's just whenever right, your big data grow too big, you need to go to him and buy a bigger server, and that way, right? You basically right, he buys another yacht using your money. So this is a problem, right? So then the relational database really cannot handle huge amount of data very economically. So this is where we have some smart guys facing this problem and decided to do something different. This is where the big data comes from. So it was actually first faced by Google. Why Google? Mainly because right in the 1990s, right, it was founded right, its goal was to try to crawl the whole world's web pages and store them somewhere so that it's ready for query. Whenever you search on Google, actually you're not querying the whole web pages in the world, but rather you're querying a copy that Google has retrieved into its database. So basically that's where. Anyway, it was indexing the whole world's web page, and clearly, right, this is ever growing, and then all kind of new type of data coming up, right, all the time. And it doesn't fit this kind of strict schema that has been predefined. And more important, right, you cannot just fit this huge data into a relationship without bankrupting your account. So this is why that they came up with a new idea. What's the new idea? It's very simple. That is, let's forget about all these schemas. Let's forget about defining tables. Once we retrieve a web page content, let's just dump it into somewhere on some cheap hard drives. So and then this is write it once, and then later on we're going to read this file out and then make sense of it. But for now, we just dump the data there. So into those cheap commodity machines. That's big data. And how do we do that? That's called Hadoop, the MapReduce system. Let me just talk to you a little bit more about that. So basically the idea is that now you have a huge chunk of data, and you're going to divide them into different blocks, even like 64 megabytes or 128 megabytes. This is one block. Then you write this block into these cheap computers, and then to ensure high fault tolerance, you are going to have redundancy. Like each block is written 3 times to different commodity computers.
Basically, those are just like servers.
Yeah, these are the data servers. These are the data servers. And then you have a name, this is called a master server, or name node. So these are data nodes. You have a master server here to kind of overseeing which block has been written to which data server. That's it. Very, very simple. Very, very easy to understand. And that's called Hadoop. That's basically, this is what is Hadoop. What is called Hadoop? Because the name of the inventors, right, sounds toy, elephant, right, called Hadoop. And that actually was invented in Google, and then later on, right, a Yahoo engineer decided to make it open source, and this is where Hadoop is. Hadoop means dividing a large data file into blocks and write them to the hard drive. That's Hadoop. That's it. It's very easy, actually, very easy to understand, right? And nothing fancy there. And the idea is extremely simple, right? Just write them there. Then what is MapReduce? MapReduce is how you use the data. Suppose this is a huge amount of data you have it here. You divide them into different blocks, and then you write them into each kind of data nodes here. Now, suppose this data is about some text. You would like to do an analysis about the word count. How many unique words are here, and what's the frequency of showing up in this text? So very simple task. So what you do is actually the first thing is locate each block. And the second, right, within each block of data, let's look at, right, this word A, then how many, right, occurrence it has. If there's occurrence, let's write 1 here. So basically this is occurrence, and there's AC another one, right? So basically different occurrence of different words. Then, so you go to write different blocks, and then you come up with all this called key value pair. Then this is called mapping. You map your task of counting the words into each data node. So this is the mapping part. Then what's called reduce? Your ultimate goal is to learn, right, in this huge, right, the whole data file, how many A are there, right, and how many different words are there. So the reduce part means that you aggregate all these 3 results together. Now you can see, right, there's a 3A, 4A, and 3As. So altogether 10 A's here. So the ultimate result will be A is equal to 10. That's called reduce. You reduce, right, the results from each data node into a single result. Basically, that's MapReduce. Nothing,
It's brute force enumeration that is enabled by cheap computing power. That's basically what it is, right?
Exactly. Actually, yeah. That's a very, very old idea, actually, right? So, but it's used in a very genius way. And at that time, right, even think about Facebook. Mark Zuckerberg was a very smart guy, but he didn't think about this at all, right? He used the relational database initially to start Facebook, and then he found, I cannot handle this data at all. So he fixed that problem. And what's really genius about Google, especially, it's Larry Page, was that he was willing to use the commodity equipment to try to save store as much data as possible. He actually went to redesign the server, the data server, and the first element that he removed is the switch, the on and off switch. He said, the server should be there on all the time, right? Why do we need to switch, right? We never turn it off. Why do we need it? So the first thing is taking that out. So this is why actually Google search engine was faster than the competitors at that time, because he was able to install a lot of data servers, right? So within the limited space. So anyway, so that was Hadoop. Hadoop means, right? So just writing the data into blocks, saving in the commodity servers, and MapReduce, right? I think in a nutshell, that's Hadoop and MapReduce system. So, so then the key idea again is that let's just move computing to the data nodes, and we do not write it on schema like relational database, but rather when we need to read the data, we will impose structure to it, and then use a parallel computing and using redundancy to achieve high reliability. Typically it's 3, right? So 3, you write the same block 3 times to keep it redundant. And all this, as Ritu said, right, this sounds like familiar. This is the lady that I admire a lot. See, right? So if you're doing Oracle, right, it's like, right, if this is not enough, let's try to grow a lot of oaks, right, so that we will be able to handle the data. So rather, right, Google came up with a very smart way of using, right, a lot more computers to achieve the same goal. So then now this is the kind of Hadoop ecosystem. So we have the Hadoop data file system, you have the MapReduce on top of it. Then there are a lot of more applications. For example, you need to get the data from a relational database to Hadoop. What do? This is where you have scoop here. This is called scoop, right? Scoop the data in. And then suppose, right, you have a lot of visits, right, to your website, and then there is a constant stream of data of server log. How do you run that in? That's called Flume. So Flume means streaming data in. And then if you want to do some kind of machine learning on the data, what is called, that's Mahout. And then so Pig is used to load the data, and Hive is trying to impose some structural query language into it. So basically, all these things should be very, very easy to understand by now. So that's my job.
You say Mahout uses sort of automated machine learning for the data that you have in the Hadoop database.
Yeah, exactly. Yeah, it's on top of the Hadoop MapReduce system. Yeah. So. And so pretty much, right, that's what we need to understand, right, at the CEO level about big data. So then these are the major vendors, right, Cloudera, Hortonworks, and MapReduce. These provide Hadoop systems that you can install. All of them are kind of free for you to download and install. They make money by providing tech support. And these days, right, most likely you're not going to buy computers and set up your own cluster, but rather you will go with one of the cloud solutions. AWS is the biggest. It's actually bigger, 5 times bigger than all the rest of the world combined. So then the second one, biggest is Windows Azure, which is actually much smaller than AWS. But anyway, so here we are.
Is that with the storages of the data?
No, we're talking about the capacity.
Capacity.
So every AWS has not only storage but also computing power as well.
Okay.
And you can set up a Hadoop cluster. You can say that I want to have 1 master node clearly and 5 data nodes. Then with such computing power, you just submit your specification. It is going to set it up just within seconds. You have a Hadoop cluster right there. It's a very convenient.
Or does it have to be within the structure of the data file? In other words, like name, address, zip code?
No, actually. So this is nothing. Okay, that's a very good question. That is, if you're using Hadoop, you don't worry about the data schema at all. You just load the data to it. It doesn't care what you do. This actually is where the name Pig comes from. Pig is used to load the data to Hadoop system. So why Pig? Because it eats everything. It eats everything. So basically the name it means that I can load whatever data and just throw it to the Hadoop file system without worrying about the schema at all. When you need a schema, that is when you read the data to make use of it, to make a meaningful use of it, then you impose some schema. Okay.
Oh boy. So
even though you're way above where my elevator stops.
Yeah.
It just occurs to me that from the pharmaceutical pharmacoeconomic analysis of data,
Yeah.
claims data,
Right.
one of the limitations was the schema of all the claims data
Right.
and the gnashing of teeth to get at really useful information. So my question to you is this: has this type of big data been adopted by? Go ahead.
That's
Jump
a
on
great.
that.
That's a great question. Okay, that's a great question. So now let me ask you, right? Will Hadoop resolve that problem? Now the answer is very clear. No, it cannot. Right? It cannot resolve that problem. It can help you say
Because of the way the data is structured in the claims data?
Exactly. It's a garbage in,
So-
garbage out. So that's-
Well, wait a minute, it's not garbage, it's just data.
I know. So what you're saying that, basically, right, if the data format, right, is not compatible with each other, and then Hadoop cannot resolve that problem at all. So actually, we're working with one of the biggest companies here, right, which has the biggest collection of all the claims data.
Yeah.
So they are using some solution, and then so actually the most challenging part is in the read part, schema on read. You need to tell your pig command that this field is about custom name, this field is the claim amount, and this field is data. You need to tell it. If you do not, one of the worst thing about a pig is that whatever you run, it will give you the results. But if your schema is not correct, then it will give you some result that's very weird. So
I just want to make a quick comment on that.
Yeah.
So, to your question about claims data,
Yeah.
the reason why it's so inaccessible for research is because the way the data is structured, as you correctly point out. And the only solution to that is to write additional code that will pull out the data and put it in the right kind of structure that is appropriate for analysis. So these solutions are not designed to handle data that is trapped in bad schemas. Okay, these solutions are basically designed to handle large amounts of data that are being generated from anywhere, dumping them someplace, and then constructing schemas that are inductively derived from the data. Right? So it's like I have just completely unrecognizable, unpatterned data lying on the floor, and then I'm going to kind of inductively impose some structure on it and see if it works. But the nice thing about it is I can keep changing it, as opposed to claims data, where there is an authority that's telling you, okay, here's how claims are going to come in,
Right.
and you're not going to mess with this.
Okay.
Above my pay
This-
grade.
Dinner
Seems like it
conversation.
is like repository of unstructured data. You just dump all the data out that you really don't care about right now, and then you figure out later on, okay, what sense can I make out of it?
Yeah.
Right, exactly. So now let me give you another quiz. Suppose you want to support online real-time transaction. Should you use Hadoop or not? No, you shouldn't. So it is really user to save huge amount of data in an economical way that you can retrieve later and do something meaningful.
Yeah, I mean,
That's big data.
So let's say you have this. So say I have 1 million patients. I got 1 million patients. They're all wearing their Fitbits. They're throwing off steps and heart rates. And then I got the same 1 million patients. I have a key. I have them in another database, and I have say their claims records, right? And so if I want to take those, put them together, and use it in this model, is that?
So yeah, so okay, now you have two solutions, right? You can just spend $10 million to buy Oracle big data database server, or you can spend $2,000 on AWS, right, to be able to store the data. However, you need to be very careful, right, about your data schema, because there might be incompatibility issues, right, from different even Fitbit devices, right? It can be different. So yes.
So these, I mean, I think it's important to point out that all of these solutions are not getting around the need for a data schema, right?
Exactly.
I mean, at the end of the day, your sense-making, analysis, insights, everything comes from, some meta-level organization of the data. All these are letting you do is to leverage the inexpensive nature of computing technology and the power processing capabilities that you have to take large chunks and dump them.
Yeah. And I'd say, for example, hi Alexis, welcome. And I'd say, for example, there's a company that's called Politic right now that actually offers sort of Hadoop as a service for wearable device data and provides integration for it.
Called what?
Politic?
Okay, so we're good? Okay, go ahead, one last question.
Okay. What benefit does Hadoop give me versus just throwing data in a bunch of regular old file structures?
That's
Dumping
great.
it all there,
So
dumping it there,
then
and then when you need it, you design a structure to retrieve.
In that case, you came up with your own Hadoop system,
Okay.
right? Yeah. The wheel has been invented, right? Just use it, right? It's open source. So yeah, I agree with you, right? Just buy 5 hard drives and throw my data to it. When I need to retrieve data, I do it. Then the redundancy issue, right? So basically, Hadoop has resolved all these issues. It automatically, divide into blocks. It automatically divide into 3 different nodes for you. So all these are.
But that's your RAID system anyway, right?
Yeah.
Your RAID systems, those silos already do a lot of that stuff.
Actually, the RAID system you're talking about more like hardware level, right?
Right.
Yeah. This actually is at the software level, right? So,
Okay.
Yeah.
What happens if I have 1 million patients and one of the data points for them is the blood pressure? And then can I query the system and say, give me the number of people that had 150 and above blood pressure?
That can be done very, very easily as long as you know how the data is stored on the
So I have to store it in some
So
format.
right.
Okay.
So
And
when
that's
you
small
store
data.
yeah.
1 million patients is very small.
I'm just
Right.
So
following
we know how to.
We just think big, right? Think big,
I'm
right?
just following up with 1 million.
Is Grace still working?
Okay.
Is Grace still working?
I think she passed away, right?
Yeah.
Someplace, some universe.
But she's amazing. So okay, so she actually, she found the first bug in computer history. It's a real bug, right? Inside the computer. The bug, debug, right? We call it debug. So yeah. Anyway, okay. So let's move on then. So basically that's about big data, and the second is about how we make use of the analysis, right, out of the data. So basically, right, for analytics in mobile health, basically, right, there are kind of traditional methods which is regression based, right? You try to correlate with X variable with a Y variable here, right? Fit a curve in between. So offensive ones like data mining, machine learning, we try to classify, this group of patients who use Fitbit versus this group of patients who do not use Fitbit, things like that. So basically, there are many, fancy tools there, but they all boils down to one thing, that is correlation. That is something that we want to really keep in mind. So, whether the roast cloning causes a sample rise or not, so that's exactly the issue, right? So, if this is even greater causality, which means that these guys come first and this guy comes second, right? So it comes. So, but it's clear there's no causality. So what we need is really causation. Why? Because for any actionable knowledge, right, you want to know whether this leads to another desirable outcome. So this is where, right, you need the causality, and the correlation is not enough. Unfortunately, right, most of the statistical methods that we will see in big data will be, even analytics, right, so generally speaking, will be more like a correlation. It produces a statistical significance, but doesn't tell you whether there's a causal inference there. So this is something that we want to really keep in mind. And many times, right, when we were buried in the data, right, and we are trying to scratch our head to try to figure out whether there's any insights in it, we will be very prone to this kind of mistake of finding some significant and believe that there is causality. Actually, there might be not. So let me give you some examples of highly correlated data. People drawn by 42 versus Nicolas Cage. Highly correlated. This is another one. Represented by Arcades versus Dr. is awarded. These are, right, the correlation coefficient is 98.5%. I don't think there's any causality between them, it's just a pure correlation. And pure correlation becomes much easier to find when you have big data. Why? Let me just give you one example. Let me just skip all this. Let me give you one example here. Like here, suppose, right, you have 10 variables. Each variable has 3 levels, right? Like low, middle, high. Like, think about that way, right? So like classify ages, right? Between, right, old, middle age, or young. Then even among these, right, you will be able to have over 60,000 subgroups, right? So you classify your data into 60,000 different ways. And you're doomed to find some significance among this kind of different partition of your data. So this very likely will be pure chance that you find something statistical significant, which might not be there at all. So basically, this actually, so leads to the second point I want to make, that is, you might want to be very, very careful about causality and use some methods called a randomized controlled trial, which we're all very familiar with.
You make a really good point. I mean, with all the big data, you can make these silly inferences, and it's very plausible. You look at a graph, yes, it is.
Exactly, right? And it's very convincing, right? So,
What
yeah.
happens if you have data sets that are different formats? Can you correlate?
That can be done as well, yeah. So we have statement analysis, right? You can just give a numeric number to even text message, right? So then you can quantify that, yes. So the key issue here is that you have big data, you have lots of data, you do some analysis, it comes out as correlation. So keep that in mind. Then how do we prove causality? That is what you need, like randomized controlled trial. Then leads to my second point about how to make the randomized controlled trial more useful. So here it is. Here is what the RCT looks like. Suppose we're in a program about using mobile phone to reduce weight, right? To lose weight. Then, so this is the treatment group with the mobile app. This is the control group without the mobile app. This is the weight before, this is the weight after, right? So then the treatment, typically what we calculate is, right, the weight after minus the weight before, that's how much weight you lose, right? Actually, this should be the other way around, but anyway. Yeah, so then the minus, right, the control group's difference. So this is the difference in differences. Then what's wrong with this? I can show you, right, in the prestigious journals like the New England Journal of Medicine, right, this is, right, published in 2011. This is about a mobile app. It's not a mobile app, actually, it's telemedicine, where, this is a control group where they receive nothing, right, no interventions. And here you have two arms of interventions. One arm is called remote support only, call people to lose weight. And this is in-person support, right? You come over to the session, that we talk about that, and you lose weight. So it turns out, right, you find that, the good news, telemedicine is as effective as face-to-face conversation. Mm-hmm. So this is published in New England Journal of Medicine, done by a bunch of Hopkins researchers. So, so now the effect, what you see here is we calculate the effect of remote support and in-person support. So using exactly the same, formula here. Now the question is, what's wrong with this method? This actually has been brought up a lot in the review. There's nothing wrong with the outcome, but it is not very useful. Why it is not very useful? That's because what we estimate here are called the average treatment effect. What is average treatment effect? It means that in that study, you have 1,400 patients, right, divided into 3 groups. So that's the average outcome of 500 patients in this arm of treatment. So given that, right, so you have the average treatment effect, but many times, right, what we need is we want to know whether, like, telemedicine or this mobile app is good for this particular patient or not. You cannot be assured that this patient belongs to this subgroup that will enjoy the benefit or not. So this is why, in recent years, a lot more emphasis has been put into the heterogeneity in treatment effects. Put into plain English, that means that subgroup analysis. So we want to understand, right, how this mobile app is going to benefit which subgroup, rather beyond the average effect. That is actually what we want to keep in mind, when we design the experiments. And more important, you want to have the subgroups pre-specified before the RCT. Why pre-specified? As we said, right, if you have the data already, if you kind of partition the data, try to look for significance, you will find some significance because there are so many different ways to combine the data to create the subgroups. So this is why it's important to pre-specify the subgroups before the RCT.
So you're saying that the 1,400 patients that Hopkins reviewed how they reviewed them wasn't accurate enough.
No, they are, yeah, they are only at average. Actually, that's a very good comment. Yes, they are not very accurate, specific to the patient level, right? This is just the average over these 500 patients who are in this, right, Kelly consulting group. They lose weight about like 4 pounds. That's it. Yeah. So, but you cannot tell whether it's a old people, right, female, are they going to benefit this or not? That you don't know.
Because it could have been the 3 groups, and then those 3 groups could have been subdivided into additional groups after X amount of time.
Right, exactly. Yeah. So this is where actually now the cutting edge in a kind of RCT is really emphasizing on the subgroup analysis, pre-specified. So pretty much right, these are the 3 things I want to talk about. Right, one is about the idea for big data. The 2 about causality and heterogeneity in treatment effects.
Normally now we report confidence intervals, so wouldn't that sort of deal with that to some degree?
That's a very good point, right? So again, the confidence interval gives you confidence in the statistical significance, but with so many combinations of permutation, you will find some significance by chance. That's a key thing. You are not sure whether
in an RCT.
Even in no, not in the RCT. RCT, if you define RCT at the every treatment effect level, that's fine. But once you have done this and you try to see which subgroup will benefit more, let me get partition my data and see. Then you will find some subgroup will benefit a lot.
So how do you disprove those correlations?
This is not correlation.
Some of the other correlations that you find that are mistaken correlations, how do you disprove them? I mean, obviously the chicken and the sun is an easy one, but some of these correlations may not be so easy.
Oh, yeah, these are the previous slides, which are pretty cool.
Oh, okay, so I missed that part.
Yeah.
Okay, very cool.
Don't worry, I can explain further.
Yeah.
So
So to your
It's like
question,
drowning in movies or something.
No, yeah.
well, I mean,
Sunspots.
so there's a couple of ways to respond to that question. How do you disprove a correlation? I mean, to the extent that we're going to have more and more big data, people are going to point to correlations as evidence, right? So the first test, if our gold standard is causality, if we can do or even construct a randomized trial from big data, which we can do, right? We can construct an experimental and controlled sample from the data itself by doing appropriate matching and so forth. So we can do that. That's one way. Second is to, just the plausibility or the smell test, as we call it, right? So the examples that Gordon presented are, clearly spurious correlations. But sometimes there is enough experience and insight amongst practitioners and other experts who can say that, I have a hunch that this is a true correlation, but all it needs me to do is to propose a formal hypothesis that I can test through an RCT, right? So it's very useful for the hypothesis generation phase, but less so for the hypothesis testing phase.
Yeah.
But see, the smell test is for humans, right? Watson will not be able to do a smell test.
Yeah,
Watson will say, don't watch any dinner movies or you're going to end up drowning.
So if you want to use Watson for knowledge discovery, you basically have Watson spit out all these hypotheses, right? And then you sort of subject them to the plausibility and the smell test, and you recognize that this is only for hypothesis generation. It's not to prove the hypothesis.
So basically, that's a practical, suggestions, right? If you have done the big data analytics and you have some very interesting significant findings, what you do first is the smell test, right? Check whether your business shrewdness is reasonable or not. Then the second step is, are we able to show the mechanism that A leads to B or not? So don't just take that, as causality. If you could not explain what's going on, then that might be difficult. That might be kind of a spurious correlation only. And then the third is, as Richard said, right, develop your hypothesis and do that in a randomized controlled trial to prove that. So.
Higher statistician.
Right. We have an MSIS program that's pumping out data scientists, you know.
Yeah. Okay. Thank you very much.
Thank you.